the recording, and we'll go through the supervised classification script. So yeah, here, this is basically a more extensive introduction into the supervised classification of text than you have just gotten. And supervised here, like in the beginning, I wrote a bit about what supervised actually means. And in our case, it means that we show the machine a data set that already contains the value or label that we want to predict, the dependent variable, if you will, as well as all the variables that are used to predict this class or value. And if we were to do regression, we would say, yeah, that's independent variable. That's an independent variable. But now, as we are machine learning people, we say features for independent variables. And in my examples here, the features are the tokens that are contained in a document. And tokens can be used broadly here. It can also be used, it can also be like bigrams or trigrams. Or if you use word embeddings, it can be the embedding vectors, etc. And in my example, the dependent variables are sentiment. I took out the author's example because it didn't work properly, and I couldn't fix the error. I don't know what the problem was. But the sentiment actually works kind of well, and I think it's basically the same task. So overall, the process of supervised classification using text in R encompasses the following steps, as you have just seen in my brief presentation. So first, we need to split the data into a training and a test set. Then second, we do pre-processing and featureization. So we basically turn the text into, we split it up into different features, and we pre-process those as well. And then in the third step, we train our model. In the fourth step, we do cross-validation and subsequently tune our model or adapt different parameters either in the pre-processing or in the model. And we repeat 2 to 4 as often as necessary. So if we're not happy with what our cross-validation reveals, we go back to the pre-processing and maybe make some changes here. Then we retrain our model, we evaluate, and if we're not happy, we go back, etc. And then in the end, we apply our model to the held out test set. And number 6 is then the final evaluation, which is we check how well the test set or how well the model has performed on the test set. And those steps are basically mirrored in the workflow function in R. Because in the workflow function, as I showed you earlier, you define the pre-processing procedure, the recipe, through add recipe or through the function add recipe, and you had to create the recipe through the recipe function from the recipes or text recipes package. So you can also do just normal regression with like numerical values or just basic statistical modeling, if you will, using the tidy models framework. And that basically works the same way as what we do today. But today we will work with text, and therefore we have the so-called text recipes package. In this version of the script, I haven't added the citations for the different packages already, but in the final edition, those will be, of course, added because like these people have really worked a lot to make these packages happen, and it's quite impressive the kind of framework they have created there. Exactly. So in the workflow, if you define the workflow, you first add the recipe, then you add the model specification using the add spec function. And here for this, we use the parse, like this comes from the parsnip package, which is again part of the tidy models framework. Here I try to pull together a bit like overview of how what the workflow looks like. So in the end, you like once you have created the recipe, you have created the model specification and the training and test data, you can just pull together the workflow like this. So in the beginning, there is the workflow function that basically says, okay, here we have an empty workflow. Then you add your recipe, which is your pre-processing procedure. You add your model, and then in the end, you can just fit it. And to fit comes also from the workflows function in that case. Yeah, and in the so let's just go through this thing here step by step. So first step would be to split your data. In like here, I just load all the different packages that we might need. So here we have, for example, glmnet, which is used for logistic regression. We have Discrim, which is used for naive Bayes, etc. Overall, I would just suggest that you copy this block. We don't need the corpus function here, but you can just copy this block, and if you run it, you should be good to go. And then here we load the IMDb data file, and the IMDb data basically looks like this. So you might know that from earlier. So here we have the text of the IMDb review, and then here we have a label, which is the sentiment. So the sentiment here means, okay, the reviewer liked the movie or the reviewer didn't like the movie. Yeah, and so now our first step is to divide the data into a training and a data set. And for this, we can use the initial split function. One important thing is that the test and training set are fairly balanced in terms of the classes that are contained in there. And in this case, the sentiment needs to be sort of balanced, because it's not useful if you have a lot of positive cases in the training set, but then there are no positive cases in the test data set. And so here we can provide like the variable that needs to be that is like important in the strata, for the strata argument, and or as an argument to the strata parameter. And here I also define the proportion, which I say is 0.8. The default value is 0.75, so it doesn't really make a difference, just to be sure that you have seen it. And then we have split it. Here we use the training function to extract the training set. So here I have IMDb train, which is just a randomized or just a part of the initial split that has been defined as a training set. And then here we have the test set. And then yeah, here I just glimpse. So here we see what the training set looks like. So it's only 20,000 rows now instead of 25,000. And what we have seen here is that they didn't shuffle it. So it might actually make sense to just shuffle the data. Shuffle. So yeah, I haven't done that before. So now the data is shuffled. And yeah, but for the rest, I actually can't do that because then I would have to run my stuff, and that just takes too long. What we also see here is that when we count the sentiment, that our data set is super balanced. So the training data is balanced, and the initial data is balanced too. Like we have 12,500 positive and 12,500 negative reviews in there. So well, we see that clearly the function took into account the distribution of our dependent variable because we provided it to the strata as a strata argument. Then the next point is pre-processing and featureization. And in the tidy models framework, pre-processing and featureization are performed through so-called recipes. And for text data, so-called text recipes are available. How do these recipes look? So usually you have, in the recipe, you just have different steps, and these different steps achieve something. So here, the first call always is recipe, and here you need to define the dependent variable, then you use the tilde, just as you do if you perform a regression, a linear regression in R. And then here you have the column where the independent variables are positioned in, or where you can find the independent variables, in our case, the text. And then here, as when you use linear models, you have to define the data that you use. So here we use the training data, of course, because we want to fit our model on our training data. And then you add different steps. And in our case, because we work with text, our first step would always be to tokenize the text. And then here in the middle, we have a bunch of different steps that we can use. So I will show them in a second. I have made a list of them. And in this case, we just do a step token filter. And through the max tokens argument, I say, okay, I want to have 1,000 tokens in there. The I1 E3 basically meant the same as 1,000. The freeze basically stands for the number of zeros that you that are added to the one. And yeah, so make sure that you always include the column that you want to work on as the first thing. And this is usually a column called text, or whatever column your dependent variable is stored, your independent variable is stored in. And then here you would add additional pre-processing steps. And then in the end, your final step will be to add the term frequencies here, or the inverse document, term frequency, inverse document frequency. So in the very end, you actually count your text or your different words. And this makes sense because it doesn't make sense to tokenize the text, then you count the different things, and then you would stem them, for instance. Because then the original tokens would be counted, and then those original tokens would be stemmed, and you would basically duplicate your different features. That doesn't make sense. And therefore, in the counting point comes in the end, because this basically gives the features a particular weight, if you will. Because if a word appears more often, it might be more important to the text in or to the document in the bag of words logic. And in case we want to see what the data set for the classification task looks like, we can also bake we can prep and bake our recipe. So in this case, we take our basic recipe, we prep it, and then we bake it. And then we see how our data look in the end. So here we just have, here we go. We have the different independent variables. So here, the way this is structured, like here we have different numbers, which don't matter to us that much. But then here we have TF text. TF stands for term frequency, text stands for the original variable name. And then here we have the name of the word. So here we have a, we have able, we have about, above, etc. So this is basically the term and how often it is present in the different documents. And so here in the first document, which is of sentiment negative, we see that those terms are present. All right. So here I have listed further pre-processing steps that you can use. I will add a link here to the vignette so that you can look them up yourself. So what is possible here? So I have added here the name of the step, and then here the most important argument. So, or arguments. So step token filter, for example, can be used to filter tokens, as you saw earlier. Step lemma allows you to extract the lemma. In that case, you would have to install Spacy first, though. So if some of you haven't been able to install SpacyR first, haven't been able to install SpacyR, you cannot use step lemma. And for step lemma, it's super important that you tokenize through SpacyR first. So in this first step where you tokenize, you have to make sure that you define spacey R as the engine. Yeah, that's just, you just have to take that into account. Because then spacey R will be used for tokenization and it will automatically give you the lemmas. And then step lemma only extracts those lemmas. Same for part of speech tags, because if you tokenize with spacey, it will also give you the part of speech tags. And then step POS filter takes the part of speech tags. And the thing with the POS filter is it doesn't only add the part of speech tags, but it also filters out words that do not have a certain tag. And by default, it only takes noun. It only retains nouns. And the rationale here is that, I don't know, a text can be classified easier if you just look at the nouns, for instance. And here, of course, you have to tokenize through spacey R as well. Step stem stems the different tokens. You can specify your stemming function through custom stem. The default is snowball pseudo, which usually works sort of fine. And then here you can use the options argument to provide a list to the stemming function. So here, for example, if I want to have, if I want to use my stemmer for Russian, I would say step stem, and here is the variable, which is text. I say custom stem snowball C, and here is my options argument, and here I need to provide a list, and the list contains of named elements that, again, are used as options to the snowball C function. So if you call the snowball C function itself, it has the argument language, and here through this list you basically provided this argument or this parameter. So here this would stem in Russian. Step stop words, remove stop words. Through source you can give it an alternative stop word list, and potential values are contained in the stop words package in stop words get sources. And you can also use a custom stop word source. So provide your own stop word list, which is basically a stop word list. In that case, is a character vector. We have language to specify the language of the stop word list. Here again, potential values can be found in the stop words get language is function. Step ngram takes into account order of terms, provides more context, as I showed you earlier. So here, the argument num tokens refers to the number of tokens in the ngram, and it defaults to 3. So by default, you would take trigrams at most. But then you also have the second function, which is minimum number of tokens. And if you do, for example, step n, so if you would put a 3 in there, it would only take, because the number of tokens defaults to 3, it would only take trigrams into account. But if you take a 2 in there, if you put a 2 in there, it will give you trigrams and bigrams. And if you put a 1 in there, it will return all the uni, bi, and trigrams. Step word embeddings uses pre-trained embeddings for words. Yeah, you probably won't use that right now, and once you are able to use it, you will be, yeah, you can use pre-trained embeddings for words, which are basically vectors instead of words, which are better for a lot of downstream tasks usually. But it's a bit tricky to work with word embeddings in R. You might consider using Python for that, actually, which I personally don't get. So maybe I should learn too. Step normalize performs Unicode normalization as a processing step. This is useful if your text is a bit screwed or if it's like a bit broken. Yeah, and then the last one, which is really handy, I would say, I would probably just do that by default, comes from the Themis package. and it's called upsample, but I think it's step upsample. And it takes care of unbalanced dependent variables. These dependent variables need to be specified in the call. Yeah, here it only has the argument over ratio, and by default this is 1, so that all the different imbalances are canceled out basically. And now we go on to model specification, and here in the model specification we use the parsnip package. Here we use this scrim, I'm sorry. So now that we have the data ready, we need to specify the model. And model specification basically looks like this. So we have different initial functions. In this case, this comes from the, not from the var package, it comes from the parsnip package. Here we have the different function, and then we need to set the mode in that case. So basically we have two modes, whether it's continuous values that you want to predict or categorical ones. So here we have classification, which predicts categorical or discrete values, but we could also use regression for continuous ones, which gives you like the raw probabilities. What the classification here does is it takes the raw probabilities and then it says, okay, it's a probability above 0.5, then it's positive. And if it's below 0.5, then it's negative. And then in the end, we need to set the engine of the function. So there are different implementations of the naive-Bayes function, for instance. We just use naive-Bayes here. And there are, yeah, some upsides or downsides to the different engines, but you, like for your tasks, these different specifications should work well. So here we can use, here is basic logistic regression, which comes from the GLM package. And here we just call logistic reg. In the beginning, we set engine GLM, and then we set the mode to classification to predict categorical values. Here we have a lasso logistic regression, which works quite well with text. I don't know if you remember or if you've visited the talk by Jan Sodoge, but he used lasso regression to classify his different newspaper articles into topics, as far as I remember. And the nice thing about lasso is that it gets rid, or it penalizes predictors that are not meaningful. So it basically gets rid of them, which increases the quality of the results. So here I called it the same here, but I would probably call it lasso spec. And we just say it's a logistic regression, but it's a mixture one model. There's also a different kind of penalized regression, which is the rich regression, which would be mixture two. But in case you want to use that and you don't remember, just look it up online or yeah, send me an email. Here we have support vector machines. Here you need to take in mind that you normalize all the predictors in the beginning. This needs to be the last step in the recipe. And here, that's just a command. And here you can either do regression or you can do classification. Random forest here, as I used earlier. So we can also do regression with this one. And then here, the XGBoost, which is probably one of the most advanced and powerful ones, but also one of the most computationally expensive ones. Yeah, this can be used for regression or classification. And this is just different specifications, but you can basically use them interchangeably, to be honest. And that's the nice thing about the tidy model framework, because it really unifies the different tasks. And this is then easily achieved through the workflows package. So here we have the workflow, we add the recipe, we add the model, and then we fit it. That's it. Yeah, and then it comes to the evaluation. So here I put in again the picture of the different folds. So here I first need to determine the fold. I use the tune package for that. And the function is called default CV. The CV stands for cross-validation. The stands for, I'm not sure, maybe vertical. Yeah, but this is basically what you do. And this gives you this, oh no, now I crashed my R. Yeah, this basically gives you 10 tables consisting of a training and a test data set. Yeah, and if you work with the different folds, you need to train models on the respective samples. And it's important that for this to work, no model must have been fit to this workflow before. So we fit a model here, or originally I fit a model over here earlier, but this mustn't be done. So I'm actually not sure if that has worked now because I just ran the entire thing. But yeah, so what we do here is basically we fit different resamples, or we fit different models to the different folds. And what is important here is that we, in the control argument, we say that we save the different predictions. And for the metrics, we need to define the metrics that we want to collect. So in my case, in order to evaluate my classification, I want the accuracy, I want the recall, and I want the precision. And as we have, so here we basically get different tables. And here we use the collect metrics and the collect predictions function to collect the metrics of the different models. So here, what we do is we basically average over these different models. So here again, our accuracy is not that decent because we only used a basic model and naive Bayes. And we see that the precision is actually quite decent because it was kind of good at predicting all the positive examples. And the recall is kind of not so decent. So yeah, maybe we should go ahead and retrain our model. So here we would also have our different predictions. So we could just collect those. So it's basically a table consisting of 20,000 rows. And what we see is that here we have different documents, and here we have the origin. Here we have the predicted task, and here we have the original task. And here I just create the confusion matrix by hand, which would then look like this. So here I do it for fold 1. So here I have 35 false negatives. I have 639 false positives. I have 402 true negatives and 924 true positives. So we could do it like that, but there are better functions, and I will show you them now. So here, so now we could go back and adapt our pre-processing recipe and do it by hand, fit a new model or try a different classifier or whatnot. And then we would reevaluate or refit our folds on our new specification, and then this would work. Or we do hyperparameter tuning using the tune package. Because in the first, because now I will try to do something better. So now I first create a new model specification. And in this case, I use a logistic regression with a lasso, because here I say mixture 1. And it has the tuning parameter penalty, which basically determines how much I penalize a feature not performing well in prediction. And there's no way we can know what's the penalty, like the ideal penalty. So we have to determine that empirically. We just impute different values and check for the model outcome. And here I set the mode, I set it to classification, and I set the engine, which is GLMNet for logistic regression. And the next thing I will play with is also the number of tokens that I include. So here I make a new basic recipe, which I tune and I call it IMDb tune basic recipe because I want to tune the numbers of tokens that are included. And here I again use set the placeholder tune. So you always put a tune in place where you want to interchange different configurations. And so here it's basically the same recipe as before. I tokenize, then I token filter, and I token, like I don't know how many tokens I remove. And then in the end, I use the term frequencies. And for defining the different parameters, I can use the dials package, which provides the handy grid regular function. The grid regular basically allows me to make a grid consisting of different hyperparameters that will then be included into these different models that will then be tuned. Yeah, you will probably just have to try it out yourselves to wrap your head around that. But it's, on the other hand, it's not totally necessary that you know that by heart. It's just like one handy shortcut to tune your models. So here, what am I doing here? I say grid regular, and then I first say, okay, I want to, here in the beginning, I want to, for the penalty, I want some values between -4 and 0. But you could also just do penalty, and then it would give you the ideal values for that. Then here for the max tokens, I also say, okay, a range between 1,000 and 2,000. And then in the levels function, I just say how many values I want for the different levels. So here I want, for the penalty, I want 2 different values. And then for the max token, I want 3 different values. And then it will train different models on your validation folds for each specification. So we will train 2 models for each respective penalty with, say, 1,000 tokens, then 2 models with 1,500, etc. So it's a lot of models that you get, but it's fine. And the lambda grid basically looks like this. So it's just a table consisting the different combinations of hyperparameters. And so now we just define the workflow here, and to fit the different models, or for the resampling, we can use tune grid here. And the tune grid basically takes our workflow, it takes the data set containing the different folds, it takes our grid with the hyperparameters, the lambda grid here, and of course we need to specify which metrics we want, and the metrics that we want here is accuracy, sensitivity, and specificity, again, as we wanted before. And then if you run this tune grid function, you get, like you basically fit all the different models. And then if you collect your metrics again, here you will get the final, or you will get a table with the results. So here, let's just do, I will just call it T so that we can look at it in the RStudio. So here now we can look at which configuration performed best. And here the mean gives me the mean accuracy. So let's sort by accuracy, and we sort by mean. Yeah, and what we see here is that there are really huge differences between the different hyperparameters. So the smallest penalty and with the most maximum tokens performed really, really well. So we had an accuracy of 0.86, which is a huge improvement over our naive base. And then here with the, we see that even with like only 1,000 tokens, it still performs quite well. And then here, we also have, like, we see that if we change the penalty a bit, it performs really, really bad. And so this definitely makes sense. And if you have, or it's a sensible thing to do. And if you have more computational power and more time, you should try even more combinations to come up with like the perfect solution. And we can also use autoplot to look or to visualize the different things. So here what we see with the regularization is that there are vast differences between the values that we use. So the smaller regularization that we have, which is -4 basically, performs way, way better than, or now the 0.001 performs way better than 1. So yeah, we can also use the show best function, which will, which is a small shortcut just to see the best results. And here we see that the differences between like 2,000 tokens and 1,000 tokens are small, but the differences between the different penalties are huge. And we can then use the finalize workflow function to actually choose the final parameters that we want to use. And we tell this that we want, like, which parameters we want by select by percentage loss. And select by percentage loss is basically making sure that you take the best approach, but you also take the one with the least computationally demanding hyperparameters. So here, if we use select by percentage loss, we say first, okay, this is our resampling object that we defined earlier. This is the metric we're looking at, which is accuracy, and then we order by penalty. And now we would take the one with the best performing penalty, which is the least computationally expensive, which would be the one here. And then we can finally fit the model and predict on the test data. And for this, last fit is the way to go, because it takes the workflow and split as parameters. So here, the workflow that we have is final lasso IMDb, as I defined here with the finalize workflow function. And here the split is just like the split that we defined in the beginning. And then once I have fitted it, I collect the metrics. And then here I actually do the matrix by R. So here I collect my predictions, final fitted, which is accuracy. Which is just the predictions that the model gave us. Then here I run the confmat function, which gives us the matrix. And here we need to define what is the truth, or like what is the true value, which is sentiment. And here, what is the estimate, which is the predicted class. And then I auto plot it and I say type heat map. And what we see here is that it performs really, really well. Like the true diagonal here is really nice. And we have few wrong predictions. So this would be the game if you want to do supervised machine learning for text analysis in R. I know that was super fast. And yeah, it's not that straightforward and not that easy, but I think the implementation in R is nice. And moreover, like, practice is key here. And here I have added some resources. So here's the supervised machine learning for text analysis in R book, which is super comprehensive and is actually written by the authors of these packages. There is more on there. You can find also more on tidy models online. And here there is also a blog article how you can use tidy models for text. And then here I have also added a blog article which adds like a basic description of the different machine learning models that you can read and then decide which model you would use. And so I will now stop recording and explain